Welcome. My name is Terry Munson. I'm founder and owner of Foresite Laboratory. We have spent the last 34 years trying to understand reliability issues. Today I'm going to have a conversation with you on understanding how residues cause problems and where they come from. One of the things that we see in electronics manufacturing is that there's multiple sources of contamination, not just outside environments, not just flux assembly, process residues, fabrication residues. All of those variables come together and create a functional effect, good or bad. So today we're going to talk through some of these issues. How do residues cause problems? One of the key things that we see visually is a hard short, a dendrite, electrochemical migration, where metal has migrated and creating a shorting condition. As you can see here in some of the photos, these dendrites are very visible. The effect that they have is one of either creating a shorting event where there's intermittent performance issues, or where there's a fuse effect where it blows open. And then sometimes it can regrow, and as long as there's enough moisture and corrosive residue all in that same location, it can continue to create a shorting condition, to the point where in some cases it creates a thermal event, where actually the board catches on fire and starts to burn and causes more damage. So looking at electrochemical migration, dendrite shorts, one of the key things is you have to have three key elements. One is a voltage differential between power and ground. Two is the effect of the moisture bridging the structure between anode and cathode. And then three, you need a corrosive residue to kind of accelerate and act as an electrolyte. By having that electrolyte, we can dissolve the metal into that solution bubble, feed it to the affected area, and then transport the metal salts that have formed. That is basically a plating cell that happens with the conditions on the electronics. And this can happen from condensing moisture sitting on the surface of a board. This can be residues that gets absorbed from the environment and pulls moisture or fluid elements in, like conformal coatings have a monomer or a wet phase. The residues can pull those kind of contaminants in and set up the same corrosion cell. The effect of the bridging condition is probably the most critical. So if I've got a thin layer of material and I get this shorting condition, I get to dry out pretty quickly because it gets really warm. So having enough condensing moisture and high enough humidity to create these conditions is very critical. And this can happen in cold environments, this can happen in hot summer environments, and this can happen in that transition time. So we see that there's a lot of issues. And when dendrites grow, they grow three-dimensionally. They grow with the solution that's there. So we have two pads, non-populated pads that grew here, and this contamination happened from a housing or an enclosure outgassed to the surface during a elevated temp humidity test. Therefore, the humidity was at 85% relative humidity. It absorbed into this residue deposit, if you will, and then set up the tin dendrites that grew across the top of the conformal coated area. This is a conformally coated hardware, but it shrinks and exposes the top edges of these non-populated areas. That created a condition that allowed these dendrites to grow. As you can see in the diagram, it grows across that surface in the gap, but then up and over the top. So you get multiple places where dendrites are forming and growing. To see what that really means, we have the effect of making a visible dendrite growth video for you, where normal electrochemical migration, we've got a power side and a ground side. You see the bubbles that are forming across the base, and we have hydrogen production. So we're creating a conductive path. We know that there's a short. Now you can see that the metal that has deplated here is growing and shorting to this interface. Now you see that it will actually short, but since we're only at 10 volts and we're at 0.25 amps of current, we're not able to carry that. So what we see is it blow open, and we see that those remnants really don't connect anymore. And then since the solution is still full of weak organic acid, it's got a 225 micrograms per square inch of adipic acid, it's continuing to feed that mechanism. That mechanism will continue to grow and short as long as there's a fluid bridging path. So that's what caused this failure, where there was residues trapped underneath this connector. It had 66 volts. It had 2.2 amps of current, and within 30 minutes, it set up a corrosion cell and caught on fire and caused a major reliability issue. Here, we're just seeing that the metal that has basically bridged has created a solid short. So we know that we have a shorting condition that's able to carry the current. But we've current limited it so it doesn't catch on fire. Where do the residues come from? We have contaminants coming from the board fabrication process step, where the fabrication is metal etch, plating, rinse water using tap rinse water from Chicago or Malaysia, Singapore. We see all kinds of wonderful contaminants in that tap water. Those residues will be deposited on the surface. A lot of times they use cascade forward systems that allow for dirtier water to be the first spray, and then less dirtier water, and then final rinse water is either RO or tap water. And so we get really dirty gray water that is the first thing that's on, hoping to rinse off some of the contaminants from the etching and plating processes. Sometimes it makes more contamination, and so there's a lot of rinsing that is needed post these processes. But the fabrication process has a variety of material conditions that need to be understood. Fabrication is a wet chemistry process. We're building layers and layers of metal etch. We're putting boards in laminators and creating a pressed high temperature condition so we can do our interlayer work. Now we then come in and drill holes and then go in and plate those holes and plate all the surface and build that copper layer up. Then we put plating over the top of that. So there's a lot of wet chemistry processes. What we need to understand is, how do those wet chemistry processes go out into the field? The solder mask that we put over to protect everything has some stages of porosity. We have to be very careful and understand how porous are the surfaces of the solder mask that can absorb these plating chemistries as well. So we have to look at those variables. The other thing that we have is fabrication on the component side. Those components will actually go through a series of overmolding, die attach, the wire bonding, but then after they overmold, they'll go through a plating process. So all the exposed metal goes through a plating process. Then if it's a going lead, it goes through trim and form. If it's a QFN or bottom terminated component, it'll go through a sawing process with RO water typically. So the parts can come in with a certain level of contamination. Then we go to assembly and look at the assembly processes, how those interact with the fluxes. And since about 80% of the industry is no clean, we have those variables all being a cumulative effect. Now we've got a surface mount process and a selective soldering process, a hand touch-up and repair or rework process, all of those introducing more levels of contamination. And in some cases, we're using a brush and some isopropyl alcohol to spot clean an area. Those areas create additional contaminants that are very moisture absorbing and very corrosive. One of the other things that we see after we go through the SMT and the wave solder process is the operational environment. Each of the areas in the manufacturing process is a critical step in and of itself. But when we start putting hardware in boxes and in packaging and ship it to a manufacturer, let it sit on a shelf or sit in a warehouse for a certain period of time, that environment adds the opportunity for contamination and moisture. Then we put it into its functional performance, and whether it's a garage door opener or a pacemaker, these things get put through a variety of operational conditions. I've got servers that have the pleasure of using forced air cooling. And so we're pulling air from a controlled environment, supposedly, across the surface of the circuit board. Well, we're using a cold zone and hot zone in many of those cases. And the cold zone will create a opportunity where in the circuit board location where the IC is the hottest, we can get little microclimates there, and we can get condensation and contaminants on that surface. So we have to pay attention to the available humidity that the part is seeing as it functions. But then we have environmental contaminants like sulfur or chlorine gas. These outgassing conditions from either air quality or from enclosures or housings or dirty drywall can create sulfur reactions and set up a corrosion cell on those. Or if we have a sealed unit and we have a gasket that has high sulfur content, we can see those kinds of failures. When we control the environments in fabrication, one of the things that we're trying to do is we're trying to control the particulate count. Everyone is more concerned about airborne particulates and debris than they are on the chemical understanding. So we have to add the chemical understanding to the residuals, both in ionic and organic residues coming from the fabrication process. And water quality is one of the biggest. And then the assembly side, we trap a lot of fluxes with these small bottom terminated components. QFNs, FETs, some of the larger caps and resistors do a great job. LEDs are great for trapping flux residues underneath the part. What happens is the outside edges of the component will be hard and crystalline. The no-clean flux will be an insulative. But the residue that's inside between the ground plane and the back of the perimeter pads on the QFNs or on the FETs, those residues are soft and gooey, and they can create very good parasitic soft shorts. And in some cases, if the moisture is high enough and the contamination is great enough, you can get a dendrite to form there as well. One of the other things that gooey flux leaves us is the ability to bridge not just pin to pin, but from the power pin to the ground plane. We can actually see the measured effect between that incoming pin or the output pin to the ground plane if there's a glob of gooey flux underneath that part. Traditional no-clean fluxes are designed to be insulated protective residues, but they only are insulated protective residues when they reach a certain transition state. When the material goes from a soft, gooey material to a hard crystalline material, we actually can measure the resistance differences in those materials. We can see a 4 to 5 decade drop in surface insulation resistance between a hard crystalline material and a gooey material, which we published on before. So if you're interested in that kind of data, give me a call. Ionic residues coming from the soldering operations where flux travels from the bottom side of the board to the top side of the board, either through a cloud effect or through vias or through the leads that it's fluxing and trying to get enough flux in the barrel to allow for good wetting. What happens is that flux comes to the top side but doesn't see enough heat. There's not enough topside heat because you don't want to disturb the solder from the first reflow process. So the residues that are there are still moisture absorbing and still strong acids. So adipic, butyric, succinic, all of these common acids used in the no-clean fluxes that require the additional thermal energy need to be properly heat activated. And so we've been counseling a lot of fabricators and assemblers to make sure that after their selective soldering process, boards see additional heat to hold that temperature of between 125 and 150 for 30 to 60 seconds, depending on the volume of material that's there and the amount of thermal mass. So we have to look at those variables. But if that flux gets to the top side and is not properly heat activated, it sets up a beautiful opportunity for dendritic growth and corrosion. Some of the tools that we use for analysis starts with optical imaging, using Keyence microscopes, Tarragona low mag microscopes. We're able to see the effects with some of those with X-ray. We use localized C3 ion chromatography analysis to determine how much contamination is in a 0.1 square inch area with a very small extraction volume of 2.2 mils. We use FTIR and XRF, SEM, EDX. So some traditional tools, but also some new unique tools. C3 and ion chromatography, by looking at contamination for a specific area on a specific part of the board between two leads, because dendrites grow in short only in one or two areas where it's critical, where there's enough contamination from whatever the fab and assembly process is put into that location. Well, I want to understand what those contaminants are where the dendrites grew, and then we'll compare those to areas where the dendrites didn't grow to determine, is this residue coming from the fab, assembly, or environment? So we can look at those variables. Ion chromatography allows us to speciate and separate and quantify the different ionic and organic residues. So we can actually look at all of those residues that we extract from the specific area, and after we've done an electrical test on those residues to see is it corrosive or not, now we can see, is the residue made up of chloride or bromide or succinic acid or glutaric acid or sodium and ammonium. So we'll look at all of those variables. One of the other things too is as we look at trapped fluxes, it's very difficult in the no clean realm as well as in the cleaning processes. Cleaning doesn't fix everything, and residues from a cleaning process also get trapped underneath these low standoff parts. So you have to make sure that once you solubilize the residues that you rinse effectively. And a lot of the inline cleaning systems and even the batch dishwasher type cleaning systems will actually create a high pressure impingement spray that will do great in the open architecture, but won't do well underneath the part. So you want to make sure that rinsing is effective underneath your lowest standoff parts and your connectors. One of the things that we kind of touched on is fabrication residues. One of the key process historic steps is hassle. Hot air solder leveling is a way of tinning the entire board and through holes. It's not as planar as some of the plating chemistry processes like ENIG or immersion silver or immersion tin, but it's a very cost-effective method for applying a solder surface to the entire copper. Well, to make that copper solderable, we have to use a very aggressive flux. An amine hydrochloride or amine hydrobromide in a polyglycol carrier is applied to the entire board and to all the holes and vias in the structure just seconds before it gets dipped into molten solder. Then it's removed, it goes through a tap water rinse, and then it goes through another series of tap water rinses to try to remove all that flux residue and minimize any of the effects of the chemistry side. They use hot air to blow the solder away from bridging locations. So as they remove the board from the molten solder, they spray hot air or hot nitrogen, most of the time it's hot air, across that surface to make sure that there's no bridging. And that's why we have the irregularity of the surface contacts. So things are not as planar. but it's a very cost-effective way of dealing with it. One of the key things when we first started doing no cleans in the early 90s was that the boards worked fine for rosin fluxes and high solids content materials, but when we switched to no cleans, we had all these fabrication hassle residues that were causing major failures and had to be cleaned much better and much more effectively. So we've gotten through a lot of that since the early 90s, but there's still a lot of boards coming from the fabricator that are dirty due to the hassle fluxes not being understood. Solder mass porosity increases because we're not using UV cure in a cross-linking phase like we used to do. We're just doing a UV bump at best, or thermal. Those porosity differences will absorb a lot more flux and hold more residue, so we have to be very cautious of how clean or dirty the boards are coming in. One of the things that we have with the QFNs, and I come back to the QFNs because if I've got a dirty board from fabrication and I've got an entrapment process where the QFN holds the gooey flux underneath the part, now I've got just the right conditions to grow beautiful dendrites in the gap between the power and ground, and we've seen a number of cases where that occurs. And we've talked about fluxes, but one of the other things that we'll see is solder paste we go through two reflow processes in many cases, and we're seeing the effects of the secondary soldering operation being cooler on one side to protect the first side reflow. And if we're doing pen and paste, now I have flux that flows through a hole across and down to the other side. That creates a condition in which the flux is now bridging the back end of the through hole lead. That's moisture absorbing and conductive. So we see parasitic shorting in those conditions quite often. And then if you put a conformal coating over it, it makes it even worse. So understanding where flux issues are, how tight they sit to the board. A lot of these QFNs will sit 0.5 mil to 1.5 mils off the board surface. So they're very tight to the surface, and they're being pulled down because the thermal vents that are in the ground plane, solder flows down and pulls that part down and pulls it really tight, and it just seals everything around the outside edges. And it makes it very difficult to A, clean, or B, let the flux properly vent. We found that between 3.5 to 4 mils, if you've got a good standoff, that will give you much better venting performance and be able to create a much cleaner condition in which the effect is less impacting. And no trouble founds, we see a lot of no trouble founds. The industry has some of the highest warranty return rates, and one of the key things are intermittent performance issues. And in many cases, the contamination on the boards are a key factor causing intermittent performance issues, where they absorb enough moisture or have enough fluid to react with, and then they're able to dry out during either the shipment back or they dry out and perform well the next day. So again, there's a lot of issues with the soft short type of failures because it's not visible. You don't have that condition where the dendrite has left you the evidence that you need to go and say, okay, this is where my short occurred. If you have parasitic shorts because of outgassing conditions, but you don't have a lot of moisture available, you're not going to be able to set up that plating cell. You're not going to be able to get the deplate and the metal transport and then the deposit of the metallization. So each lead needs to work in its isolated design, electrically designed state. So if I have a lead and I've got another ground plane or another lead next to it, I can easily have a flux path that's allowing the residues to form across that flux path or across the body of the component because the component came in dirty. If I have BGAs that go through a water-soluble paste flux to attach the balls and it's not rinsed properly prior to the assembly no clean step, then I can have parasitic pathways ball to ball on the component side. So no trouble founds are a constant reminder that we need to understand the issues on the effects of what chemistry goes together into our final product. We get a lot of solderable, solder de-wetting issues, and in many cases we find that those residues that are impacting the solderability come from the fabrication process, both in the component and in the board level. And one of the key variables is soluble silica in the tap water depositing on the fresh metallized plated areas. And you won't be able to easily see these. Sometimes you'll see discoloration or slight hazing in the area, but the amount of soluble silica is a very thin amount, and in some cases it sets up a de-wet condition where solder just doesn't wet, or it wets and pulls away. And in other cases where the plating prep step, say for ENIG, the nickel layer was not properly done, you'll get de-wet and separation between the gold and the nickel layer. So we have to be very cautious of how they're properly processing the ENIG and the immersion silver and the immersion tin. So looking at those pads from a chemical perspective and from an oxide perspective. Some of the issues that we see consistently is, solder wetting, and a lot of people think that adding more flux will solve this problem. Therefore, we compound the amount of contamination that we do because now we're adding flux from the top side for a through-hole area that has solder de-wetting issues. We need to understand some of the thermal management issues. So we need to look at a variety of the key processing variables. It's not just a contamination issue or a thermal issue. Sometimes it's both. Looking at some of the other solderable variables that we see, they become a deposit effect, where there's just so much material that the surface has oxidized during either the first reflow or the second reflow or the selective wave solder process. So all of those become variables that impact those performance conditions. So solder de-wetting does cause problems. It's not something that's an intermittent performance issue unless there's a poor solder connection. So coatings, adhesion loss, one of the things that we see regularly is material absorbed into the solder mask that then outgasses later on after the cure of the material because we're not drying things out as well. So we've got moisture issues, we've got flux trapment issues from hassle or plating chemistries trapped in the porosity of the solder mask. So we have to look at those variables. The other thing is we can actually get dendrites to grow underneath the conformal coating. So between the board surface and the conformal coating, we've actually seen dendrites grow in many cases in sealed pumps or in sealed systems where the moisture concentration can be pretty high, and if things operate in a warm state, you get a lot of micro condensation that's occurring, and it'll pass through some of the silicone coatings and even some of the urethane coatings. If there's a residue for it to react with under the surface of the coating, it will create a shorting condition. One of the other variables that we see in the operational environment, and we're seeing more and more of these days, is the effect of sulfur. Sulfur from a variety of sources, whether it's environmental in Asia and in India, in places that have coal fire furnaces or coal fire air quality effects, areas around volcanoes. All of those have the opportunity to deposit high concentrations of sulfur. The sulfur then reacts with three things. It reacts with copper, it reacts with silver, and it reacts with indium. In our LEDs, we have silicone lenses, and silicone likes sulfur, and sulfur will pass through and actually collect in these silicone surfaces, whether it's a conformal coating or a lens on an LED, and it will pass through and react with that surface. The silver will pit and change. The indium will corrode, and typically we'll have, in an LED, we'll have indium layer with a wire bond over the top of that, and so it'll create a interface issue, and the wire bond will lift on the indium interface. The silver will corrode and short internally. We've measured, using LIBS analysis, different concentrations of sulfur inside the silicone, inside a lens, from a sealed system where they had sulfur-rich anti-vibration foam around the LED. It outgassed sulfur in a very short period of time, and then it caused the LED to fail miserably. And we were able to recreate that in some of our testing. One of the things that copper does is it reacts with the available copper, even pulling out from underneath ENIG. We can actually create a conductive creep corrosion copper sulfide crystal, and they'll pull together and they'll bridge, and they'll create just a shorting condition in a dry, sulfur-rich, non-powered environment. So this is not like electrochemical migration. It will just grow radiantly from the source and feed to the surrounding area, and then as they grow together, they bridge and create the shorting path. So if you've got a battery-powered circuit, it doesn't matter. It doesn't require that. We also see sulfur reacting with silver on resistors. It will actually pass through. There's a layer of epoxy, and there's a silver layer underneath at the interface, and this is the primary connection to the resistive film material. Well, sulfur will pass through the thinnest part of that epoxy and corrode open, and we'll see copper or silver sulfide corrosion, and it'll change the value of the resistor or take it to the point where it's open. So we see those effects. Here's the worst case of silver sulfide crystal formation that I've ever seen. This is evident that there is a lot of sulfur reacting with that surface underneath that layer, protective layer of epoxy. And metal whiskers. Everyone has heard about tin whiskers. We've also seen zinc whiskers. We've also seen lead whiskers on high lead content solder. But tin whiskers are the biggest concern that the industry had when we made the switch to lead-free alloys. Having a small percentage, 3% lead, does a great job of reducing the stresses internal to the solder material, and you have less whisker formation, either solder or plated. We have a lot of tin plating. We have a lot of structure. We've seen a number of metal whiskers inside of some of the camera connector mounts. We've seen a lot of structure where the metal whiskers form in the solder joint and grow out of the solder joint on a lead-free alloy. So we have a number of things that contamination feeds to. Metal whisker formation is primarily driven by stress, but also we believe that there's a strong correlation to the amount of contamination that feeds to the solubilization state of the metal that feed to the whisker formation. So you have to investigate more as to what that risk level is for whisker formation. And with that, I want to thank you for your time. I appreciate everyone's attention. And if there's any questions, please give me a call. My name is Terry Munson. I'm at Foresite Inc. at terrym@foresiteinc.com. Thank you.